So in our previous video, we looked at the enthalpy change of a combustion reaction using the individualized bond energies between bonds within a molecule and then multiplying that by the number of molecules within the reaction and then subtracting the products of the bond energies of the products from the bond energies of the reactants. From here on out, we're going to do this in our analysis of enthalpy and entropy and Gibbs energy. Much more simply, we're going to take advantage of those handy thermodynamic tables that we have in the appendix of every chemistry book, including yours, where all of those individual bond energies have been pretty much crunched down to a single value for kilojoules per mole of one particular substance. And that's how we'll do it from here on out. Much less calculating to do. So if you look in the appendix of your textbook and pretty much any chemistry textbook's appendix, you will see a standard table of thermodynamic values for the change in enthalpy, change in Gibbs free energy, and then instead of kilojoules per mole, joules per mole entropy. And we do is we use those values that have been listed, and we go ahead and tabulate them as we're doing here, and we make sure that we are using the right value for the substance by the state that it's in. Some tables in some textbooks will have solid, liquid, gas for as many of the substances they list as they can. Others, it's a little less, but always check. For example, water, very typically they will have the enthalpies as a solid, liquid, or gas. In this case, all of these are gases. Make sure you're looking at the standard enthalpies, kilojoules per mole, in the correct state, not just the correct substance. We'll see for methane in our textbooks, it is negative 75 kilojoules per mole. That is the standard enthalpy of formation. That's not value is telling us we're looking at 25 degrees Celsius, 1 atmosphere, and because most classrooms around the world are fairly close to that value, we can pencil those in. If you're dealing with chemical reactions that significantly deviate from those conditions, then these values don't apply. But that not assumes we're looking at a standard condition, and that F is for formation. So we have negative 75 kilojoules per mole for methane, but we curiously have 0 for oxygen. Why is that? Oxygen, along with all elemental forms of substances, will register a 0 value for enthalpy and for Gibbs. And so we can always kind of make that assumption, but it doesn't hurt to check anyway if you can't remember that rule. And then on the product side, we have negative 393.5 kilojoules per mole for carbon dioxide, negative 242 kilojoules per mole for water. So what we simply do is we take the products and we sum them up times their coefficients minus the sum of the reactants product against their coefficients. And notice how that is the reverse of the bond energies method of calculating enthalpy change. So please make note of that. Pretty much for the rest of this class, we're going to be doing it from tables. And so I always think of this in products minus reactants. So we just simply do take our values. We have 1 molecule of methane times its, products. 1 molecule of carbon dioxide times its standard value, 2 of water times its standard value. We sum those up. We have the product total. It's a negative value, and we subtract it times the reactant value, 1 molecule of methane times the standard value, and then of course oxygen registers as 0, products minus reactants. Notice that negating a subtraction makes it basically adding, so you could say negative 877.5 plus 75. You could put it that way in your calculator, and we get a total exothermic reaction. It's a negative enthalpy change, negative 802.5 kilojoules per mole. All fossil fuel combustion reactions will always be exothermic in nature because we want heat. That's why we burn fossil fuels. So once again, the difference between using the bond energy calculation and standard values from a table is where the bond energy calculation is a reactants minus products, whereas using standard thermodynamic quantities from an appendix table is a product minus reactant. So what is this actually telling us? This is telling us how much energy per mole is either being absorbed in the reaction or given off in the reaction. Once again, exothermic reactions are giving off energy from the system, whereas endothermic reactions will be absorbing energy from the surroundings into the system.